potentially be the better tool. So for the second derivative test to work, f prime of c has to equal 0. This means that c is a blank. No, not a constant. If f prime of c, with c being a constant, sure, c is a constant, but if f prime of c is 0, c would have to be what other description besides just a constant? A critical number. Yes, there we go. Critical number, critical point. So presuming that that's true, here is the second derivative test. If f double prime of c is negative, that means that f is concave down. And if f is concave down around a critical number, then that critical number would have to be a min or a max. Wouldn't it have to be a max? So I've drawn a graph of f over here. So can you see how we've got a critical number right about there? Like a horizontal tangent line right about there? And do you see how around that horizontal tangent line the graph of f is concave down? So you can see it's a relative max. Okay, so then the other piece, of course, if f, oh, you know what? Yeah, that's what I wanted. So if f double prime, I thought there was a typo. You ever do that to yourself? You think there's a typo and then you confuse yourself. You're like, oh, no, wait, it's all good. It's all good. If f double prime is positive, that means that f is concave what? Up. And if f is concave up, f had better have a relative blank. Minimum, that's right. Again, you can see this graph of f right here. You have a clear critical number there, clear place where f has a horizontal tangent line. And around that horizontal tangent line, f is concave up. Therefore, you'd better have a min, right? Relative minimum. So again, I just want to point this out to you. If you were doing a question like this, you could have used the first derivative test. Couldn't you say that maybe for the first one, f prime went from positive to negative? And if f prime goes from positive to negative, don't you have a max? We said it a different way. We said, you know what? F double prime is negative. Therefore, we have a max. So we're just using a different tool for the same job. You ever been to Home Depot and seen how they have like 50,000 different paintbrushes? You ever just sat there and like looked at them? Like I've done a lot of painting, and you look at them and you're like, well, okay, this one is for that, and that one is for this, and this one has an angled thing, and this one's only 2 inches wide, and this one is 5 inches wide. What are they all? They're all paintbrushes, aren't they? They all have one purpose, and that's painting things. But based on the design, they do it in a different way that might be more advantageous, depending on what you're doing. That's what this is. Second derivative test might be a better way, depending on what you're doing. Okay? Yeah.
I kind of have a question. So you know how like when we do like those f primacy and
Yep.
how we look at the x-axis and it's like positive, negative.
Yep.
What for f double prime of c? Like what do you look at, I guess, to determine like negative?
You would look to see if f. So are you saying if you have a graph of f double prime?
Yeah.
You would just look to see if f double prime is positive or negative around that critical number.
Isn't it all positive up there though? It's like it wouldn't be.
So we got to be really specific. Which graph are you talking about?
Number one.
Okay, so the first graph you said, isn't it all positive? Isn't what all positive?
The f of double or f of. What, I'm confused what graph this is.
So it's a graph of f. I put an f up there at the top. It's not on your paper there. I said, hey, that's a graph of f. And so, you know, you can see pretty clearly that f is concave down.
Yeah. Okay, never mind. I thought this was a graph of f double prime.
Yeah, there's a graph of f. And then, so your question is, you're starting to ask all the right questions, right? You're like, well, wait a minute. What is this a graph of?
Yeah.
Because if I told you that was a graph of f prime, it would make a huge difference. If it was a graph of f double prime, it would make a similarly huge difference. It's a graph of f, so it is what it is.
Like, what would this graph look like if it was not double prime?
Great question. So let's go step by step. To get f double prime, don't we need a graph of f prime first? So my graph of f prime would look like this. Ish. Right, f prime went from positive to negative.
Yeah.
And I'm presupposing this is parabola-ish. Again, I don't know. Then ironically enough, here in a lovely green color, this would be the approximate graph of f double prime. So we might look at that and say, wait a minute, f double prime is always negative. Yeah. Isn't f always concave down? I'd say something like that. So then what you would do, I mean, depending on what graph you had, let's say that I told you that 3 was a critical number of f, right? I told you, hey, 3 is a critical number of f, but then all I gave you was this graph. You know what you would do? You'd say, all right, well, if 3 is a critical number, isn't f double prime always negative? Therefore, f is always concave down.
Yeah.
Therefore, you've got a max at the critical number. So, like, the thing you're wrestling with is super important because you're wrestling with, what do I have, and what does it mean?
Yeah.
Those are all the right questions. Have I answered at least that one? Okay, cool. All right, anybody else? Okay, fair enough. So if f double prime is positive, we know that we have a relative minimum. If f double prime is negative at the critical number, we've got a relative maximum. But if f double prime of c equals 0, the second derivative test does not tell us anything. It literally tells us nothing. I'm not withholding any information for you. It just means that it doesn't apply here. And so c could be any of the above. And in that situation, instead of using the second derivative test, if we did get this equals 0 piece, we would actually then turn back to our other tool, the first derivative test. That makes sense? So if you try to use this and it doesn't work, you say, that's fine. I'll just use the first derivative test instead of the second derivative test. Yes, ma'am.
Should we opt for using the second one first?
It depends on the situation, and I'm going to explain here in a second like what your decision process maybe would look like.
Okay.
Okay, so let me scroll here a little bit. Before I erase this stuff, do you have any further questions? Okay, cool. Let's do this last one, and I want to kind of take you through this, and we'll talk a little bit about Young's question about should we start with this first, or should this be our last resort, whatever. So here's the deal. You see example number 5. It says, find all relative extrema of f using the second derivative test. Here is, let's talk about this right now, Young, because when it says find all relative extrema, I'm hoping that you would think, oh yeah, relative extrema, that's critical numbers, and then either the first or the second derivative test, right? And so we're going to decide early on what is going to be our path. And you might find you make a decision early on, and later on you're like, do I change my mind? I would rather use this. But here's how you make your decision. Look at the function itself. In this case, it's a polynomial, right? And you want to ask yourself, how difficult or easy will it be for me to find my second derivative? And this is where there's shades of gray, right? Because I might ask you and say, hey, do you think that would be really, really easy to find a second derivative? And you'd be like, yeah, I don't know, I don't think so. And Heather's like, no, I think it would be really easy. Well, you know what? Heather probably should use the second derivative test, and maybe you'd use the first derivative test. That's okay. Unless you're directed to use a specific one, then you kind of could pick. And there's going to be plenty of room for that, for sure. And I promise I'll never direct you to use the second derivative test when it's the worst of the two options. Right? Or I'm like, hey, this would be extra difficult. Let's make them do that. If I direct you, it'll be to say, hey, you know what? This can be easier. Does that make sense? Mm-hmm. Okay. So let's go ahead and do this. Keep this in mind. This is super important. What are the candidates for relative extrema? They haven't changed from before. Critical numbers. And critical numbers are where? F prime.
0 or
That's right. So where sometimes people will get confused here is they will say, and I want you guys to hear me clearly on this. I'm going to try to communicate as clearly as possible. Sometimes people will say, bless you, they'll say, hey, I want to use the second derivative test. You really listening right here? Because if you just catch snippets of this, you're going to be super confused. So try to hear the whole thing. Sometimes people will say, I want to use the second derivative test, so that means I have to set the second derivative equal to 0. That's completely false. Relative extrema come from one place and one place only. Where does f prime equal 0 or dne? Make sense? No matter which test you're using, you're still finding critical numbers. Critical numbers are still where f prime is 0 / doesn't exist. Okay? So that's what I've set up here. I found my first derivative, and I'm about to set it equal to 0. I am not concerned about dne here because it's a polynomial, right? Okay, so then we solve this. Number of ways to solve it. To me, factoring makes a lot of sense. And what would it be? It would be -1 - 7, like that. Yeah. So you factor it, and then you solve. So x equals 7/3, x equals 1. So what have I found so far? I have found something. I found critical numbers. So these are my candidates for relative mins or maxes. And so now this is where I have a choice. Not really, because this says use the second derivative test. But if I wasn't given that imperative, then I would have a choice, right? I could say, you know what, I feel like using the first derivative test, or no, maybe actually I feel like using the second derivative test. Let me explain why second derivative test would be better here, or faster. Maybe that'd be the better way to put it, easier or faster. I look at that and I think, you know what? I can find that second derivative in like 3 seconds, right? So I'm going to do that. And I'm going to say, all right, f double prime of x equals 6x minus 10. Now I'm going to use my second derivative, and here's how I use it. I'm going to take my 2 critical numbers, the 7/3 and the 1, and I'm going to directly plug those in to my second derivative. So check this out. I'm going to write f double prime of 7/3 equals, what do you think? What would that equal? Sorry? 4. Yep. So f double prime of 7/3 equals 4. And 4 is a nice number, and we want to be accurate. But what is the most important thing about 4? It's a positive number. So I'm going to put that in there. So f double prime 7/3 equals 4, which is positive. Therefore, I'm going to chain a couple things together here. So therefore, f is concave up at x equals 7/3. Therefore, f has a relative what? Minimum. There you go. And if you want to draw out a little quick sketch of what f would look like or whatever, like if you just want to be like, oh yeah, concave up, that means that would be a minimum or something along those lines, you're always welcome to do that. Make sure you're getting those words down accurately as well. Okay, then we just examine the other critical point. We'd say f double prime of 1 equals negative 4. What's the most important thing for us about that number? It's negative. Therefore, f is concave what? Down at x equals 1. Therefore, f has what type of extrema? There you go. Okay. So, I don't know, let me try to convince you that at times this will be better. Did you notice we only had to test out 1 number each instead of 2? Did you notice we didn't have to do a sign chart or any kind of organization like that? We just plug those critical numbers directly back in and we test the second derivative. And as we test that, we can just make a direct conclusion. To be honest with you, you don't even have to put this if you don't want to. I mean, I think this is good to put because I think it helps you connect. You don't even have to put that. And if you do, that's great. Be really careful about saying, listen to this really quick. What's wrong with this? F double prime of 7/3 equals 4, which is positive. Therefore, concave up at 7/3.
You're not saying what is concave?
Yeah, I need to say what is concave up, because at this point I've got 3 different functions on my paper. I've got f prime, I've got f double prime. And for me to just say, therefore, concave up, or therefore is concave up, or something like that, I am not being clear at all as to what I'm talking about. So again, like I said before, you want to be like super nerdy about saying someone's name, right? Hello, Jane. Jane, how are you today, Jane? Jane, I hope you have a good lunch later on today, and Jane, I hope the rest of your day is good. Jane, drive home safely. Jane, see ya, Jane. Right, you want to like say the names over and over and over to make it clear to yourself and whoever's reading your paper who and what you're talking about.
So is the second derivative like only really important if you don't want to do the like that line thing?
Second derivative test, so I think there's two reasons that would sway you towards the second derivative test, and that is if the second derivative is easy to find, therefore maybe evaluating would be pretty quick, and so you'd evaluate fewer numbers. You don't have to organize yourself with a sign chart, right? And to me, like visually, it makes a lot of sense, right? You're like, hey, concave up on F better be a minimum. Concave down on F better be a maximum.
Because then you don't have to prove if it's like increasing or decreasing.
Yeah, you don't have to prove anything is increasing or decreasing or positive to negative or negative to positive or nothing like that. All you have to do is just show a single number that leads you to a conclusion. Now, when would the second derivative test be the less desirable option? when finding the second derivative is a major pain. If you look at that second derivative and you're like, oh, this is going to require a quotient rule with 3 different chain rules in there, and it's only going to get like larger and larger as I do this, maybe it'd be a better idea to use the first derivative test. Does that make sense? I mean, really, you're going to make, for the most part, you're going to get to make a judgment. I would tell you that I'm probably a 50-50 split, literally. I think probably about half the time I think one's easier, the other half the time I think the other one's easier. You might have a different opinion, and that's okay. Okay, any other questions? It's all been very good questions. No? Okay, cool. All right, so I want to do a little bit in 3.5 here. We'll definitely wrap 3.5 up tomorrow. If you guys would, just roll ahead real quick. Hey, there's another key takeaway, right? Second derivative test, a key takeaway. Okay, went too far. So we did have a brief intro video about limits at infinity, which that in itself is kind of like a hard phrase to swallow because you really can't get to infinity. If you watch the intro video, you know that it's talking about long-term behavior to the right edge of the graph as well as the left edge of the graph. If for whatever reason you didn't get to that intro video, you'll want to. Within that intro video, there's these rules for limits at infinity, and then the rankings. The rankings thing is, I don't know, I think it's sort of interesting and will be a huge help to you to be able to do things quickly when you encounter certain types of questions. So what do I have here? 5, 6 examples. Let's just do a couple of these. So I'm going to give you guys a very definite process. I want to connect this to something that you guys also did back in pre-calc too. There's a way to do this based on a little trick you might have learned in pre-calc. I'm going to show you a couple of different ways. Okay, so just kind of piggyback off the video. When you see something like this, the limit as x heads towards infinity, what we're basically talking about is what is happening on the way far right edge of the graph. Right, as I walk way to the far right edge, the positive side, as I just keep going and going and going, what's the pattern? You can't say, hey, I've reached this point, infinity comma 2 or whatever. No such point exists, right? But what you can say is x gets really huge. What are the y values doing? Right? We're just simply, again, limits are looking for a pattern. That's all we're doing. So there's a couple different ways to do this. I'm going to show you, I'm going to just admit this straight up. I'm going to show you the more rigorous way, and then I'll show you the trick. Okay? And on a multiple choice, if you know how to use the trick efficiently, these will be really quick. They'll be really, really easy for you. So here we go. If I am going to do this the rigorous way, or one of the more rigorous ways, here's what I'm going to do. I am going to identify the degree of the denominator. The degree of the denominator is 2, right? It's unfortunate there's an extra, you might be confused to think the coefficient's the degree. It's not, right? It's the exponent. So here's what we do. We are going to maintain this limit, and I'm going to divide every single term in the numerator and the denominator by x squared, the degree of the denominator. So it would look something like this. Here's my original fraction bar.
Are we going to have to know how to do it this way always, or can you just...
Well, if it's a free response, yep. If it's a multiple choice, you can do it a trickier way. I would pay attention to this for sure.
We can't use the trick?
No, you can't just say, and my reasoning is I used a trick.
Well,
It's not going to fly.
oh, yeah.
Yeah. Okay, so here we go. X squared over x squared plus 3 over x squared. Again, I'm just dividing everything through by the x to the degree of the denominator. So down here it would be 2x squared over x squared minus 1 over x squared. It's lagging. Oh, there it is. Okay, so once I've done that, I'm going to simplify all the things that I can simplify. So it's going to be the limit as x heads towards infinity. Here's my fraction bar. It's going to be 1 plus 3 over x squared over 2 minus 1 over x squared. Just canceling out the x's and x squareds where possible. Make sense? So once you've done this, you can apply the limit. And this is where, if you learned what you need to learn from the video, hopefully this will make a lot of sense. Let's focus on this fraction right here. As x gets really huge, heading towards infinity, what is 3 over x squared approaching? 0. That's right. If the top is held constant, the denominator is getting bigger and bigger and bigger and bigger, the overall fraction, in this case 3 over x squared, heading towards 0. So I'm going to say this equals 1 plus 0 over, let's do the same thing in the denominator. The 2 doesn't go anywhere. If I evaluate the limit as x approaches infinity of 1 over x squared, again, top held constant, denominator getting really large, squared, what is that fraction heading towards? Heading towards 0. Oh, 1 plus 0 is 1, 2 minus 0 is 2. I end up with 1/2. So this is basically talking about the horizontal asymptote heading out to the far right edge of the graph is going to be 1/2. Okay? And so if you remember from pre-calc, there is a little trick to finding horizontal asymptotes. And so this is going to be the trick version of this. Here's how this works. Tricks only work if you understand the conditions for the trick. What's the degree of the top? What's the degree of the bottom? Here's the pre-calc trick. If the degrees match, then the long-term behavior to the right, and or the left perhaps, but the long-term behavior to the right in this case will simply be the ratio of the lead coefficients. So what was the lead coefficient in the top?
1.
And the ratio of the lead coefficient in the bottom? 2. Or excuse me, the lead coefficient in the bottom is 2. The ratio is 1/2. Make sense? Let's do one more then. Let's take a look at number 2. And we'll see another version of this. Yeah, I like this one. All right, so with this one, I am going to, once again, I'll show you the more rigorous way, and we'll talk about the trick. Actually, let's do it the other way. Let's do it the other way. See if you remember the trick. What's the degree of the top? What's the degree of the bottom? So the pre-calc trick says that if the degree of the top is less than the degree of the bottom, then the long-term behavior goes towards 0. So if you know the trick and it's a multiple choice, it's going to take you that long. If you don't know the trick, you want to use the more rigorous way. There's other ways even beyond this way. And here we go. So what I'm going to do is I'm going to identify the degree of the denominator. And the degree of the denominator, of course, is 3. So I'm going to divide everything through by x to that degree. So it's going to be 3 over x cubed minus 2x over x cubed over 3x cubed over x cubed minus 1 over x cubed. Andy, what on earth are you doing? Surfing the internet?
No, sorry.
Bro,
Something about colleges.
that's like ultra JV right now. Come on, get with the program. I'll wait.
I was here.
Oh, you're here?
Yeah.
Okay. How do you take notes? Is that a touch screen?
It's not.
So how do you take notes?
I can't take it.
Good Lord. Please don't make me do this. This is not a joyful part of my job, the policeman part, not the fun part. Your job is not to make my life fun, but my job will be to make your life miserable until you get with the program. How about that? Okay, so let's do some canceling. Limit as x approaches negative infinity, and nothing cancels up here. You end up with 2 over x squared there. This is a 3, and that's nothing cancels there. So we're just canceling out all the stuff we can cancel. Now, if you understand how these fractions will work, this will finish pretty quick. Let's focus on the first one. If you've got 3 over x cubed, the top is held constant at 3, but the denominator is getting gigantic, that fraction is heading towards what number? 0. So 0 minus, what's going on with this other fraction? That's another 0, right? Top held constant, denominator getting huge. And that actually goes pretty well with the answer, we think, right, based on the trick. In the denominator, you got a 3. And then 1 over x cubed as x gets gigantic, we're heading towards 0. Well, look at that. 0 divided by 3, amazingly enough, equals 0. You're going to find the pre-calc trick will fall apart when you get to an example, I think, like number 3. Number 3 is the degree of the numerator bigger. Yeah. Well, let's handle that one next time. You'll find that the pre-calc trick, a little shaky with that one. I'll show you what we could do with that. So anyways, Audrey, why don't you head on out?